All right, guys. So in this video, we're going to be talking about is the cup problem, where in our cup we have a fluid which has the same height in the cup, which is a height in the cup which is the same as the radius of the cup. And what we're going to do with that cup is we're going to spin it at some speed so that the fluid will go straight all the way to the top of the cup without spilling over. So let me turn my ringer off of my phone real quick. Okay, so what's going to happen here is we need to label what's going on within this cup. So obviously the first thing we're going to notice is the depression right here. We're going to label the depression height with D. The total height of the cup we're going to label with H, and then the height from the depression line to the top of the cup we label with HR. So the first step to solving this problem is equating these two volumes. Now, since no volume is lost, we know that this volume right here, labeled as V1, and this volume in here, labeled V2, will be the same. So V1 will equal V2. So that's our first equation. Now, our second equation will be equating the heights. So our big H is going to be equal to HR plus this height down here. Now, to get this height down here, we're going to need to take our original height, R, and subtract the depression height. So we're left with plus R minus D. So that's going to be our second equation. So what's going to happen now is we're going to start with volume 2. So we have this area right here, where in the center the volume is 0, and at R, some point over here, this volume will be dV. So it'll be easier to do this in a top-down perspective. So we're going to have a little circle in here. That is, thickness is defined as dr. So at some r, and at a thickness of dr, this will be our dV. So say we were to cut the shape right here and stretched it out. We'd be left with something that looks like a rectangular prism. To get the volume of this rectangular prism, what you need to do is you need to multiply the depth times the width times the height. So our width in this will be the circumference of the inner circle. So 2 pi r. The depth is dr. And then the height will be the height at that r. So to find the area, to find the volume at this specific r will be 2 pi r times h times dr. So we take the integral of both sides from 0 to final volume, dV. It's going to be equal to 2 pi times the integral from 0 to big R, because that's going to be our max radius right here, max radius, HR, dr. Now, the reason the h has to go in the integral is because as r goes towards big R, it's going to happen is H is going to increase all the way until it reaches HR. So we have to get H now in terms of radius. So to do that, we're going to go to our good friend pressure. Now, as we go in this fluid, remember that the relationship between pressure, that looks like an R, hold on. So remember that pressure, I think I did it again. Pressure, it will be changing with respect to radius. Because as radius changes, height will also change. And then to find that pressure relationship with radius, we'll be using density multiplied by angular velocity squared times the radius. So since we have radius on this side, we're going to have the change in pressure is equal to density times angular velocity r dr. Now we take the integral from 0 to p and 0 to corresponding radius. So we have pressure is equal to density omega squared r squared over 2. Now we have pressure here, but remember in the last video where we talked about how in a fluid, the deeper you go, the higher the pressure is. It's an H right there. So remember, we found the equation where pressure is going to equal density times gravity times the height. So we plug this in here. We have density times gravity times height is equal to pressure density omega squared, which is angular velocity squared times the radius squared over 2. Now we want to get H by itself. So to do that, we're going to get rid of the density because they're on both sides. We're going to move gravity on this side. So we have H is equal to omega squared r squared over 2 times gravity. So what's going to happen now is we're going to plug this into here. And what's going to happen is you're going to notice the 2's will cancel out. And we'll be on the left with pi omega squared over gravity times the integral from 0 to r of r squared times r, which will become r cubed dr. Let me go ahead and get some more space down here. So our volume is going to equal pi omega squared over gravity times r to the 4th over 4. Now we go back to our original equation for volume. Remember, V1 is equal to V2, and V1 is just a simple cylinder. So our radius is big R, be pi r squared, and then the height of that area is just d. So what's going to happen now is we're going to set these two equal to each other. So we have pi r squared d is equal to pi omega squared over gravity times r to the 4th over 4. So notice in this equation we have omega, our angular velocity. And on this side we have d. And if you remember in one of the previous equations we wrote out, h is equal to hr minus plus r minus d. So if we can get this in terms of omega, we will have a way to calculate the omega in terms of height of the cup. So what's going to happen now is we're going to get d by itself. So the r squared will go away. We'll leave with r squared on this side, and the pi's will cancel out. So we are left with d is equal to omega squared r squared over 4 times gravity. And now notice we have one more term that needs to be put in terms of omega, hr. So as you can see our equation up here, h is just omega squared times r squared over 2 times gravity. So to get big R into this, because we have big R and D, we're just going to set R equal to big R. So R is equal to big R is equal to HR, which is just going to be angular velocity squared, big R squared, radius of the cup, remember, times 2 times gravity. So our H is now equal to omega squared R squared over 2G plus radius of the cup minus our depression height, which is now omega squared R squared over 4 times gravity. So remember, this was HR, and this is depression height. Go ahead and get more room down here. And so what's going to happen now is these two will combine. So we're going to be left with H is equal to omega squared R squared over 4 times gravity plus R. So we want to get the R on this side. You want to get rid of the 4G on the denominator now and bring it to this side. So we got 4G, the omega squared R squared. So now we want to get rid of the R squared on this side, bring it to this side. We have 4G over R squared times H minus R. This brings us to our final step of square rooting omega squared to give us our angular velocity, and then there's square rooting this side. So this will leave us with 2 over R times the square root of gravity times the height of the cup minus the radius of the cup. This is going to be equal to omega. Now, if we plugged our height of the cup and our radius of the cup into this equation, we'll be getting the omega max of the fluid. So by plugging in the H and the R, we'll find out how fast we can spin this cup without any of the contents leaving the cup. So with that equation right there, I'm going to go ahead and leave this video here. If you have any questions or comments, feel free to leave them down in the comment section. But otherwise, I will be seeing you guys in the next video.